Hi dear students, so I hope all of you are preparing really well for your KCET 2025 examination. So today we are going to do the one shot of the chapter classification of elements and periodicity in properties. So this is a very small chapter and the weightage is not also very high, but yes, one or two questions can be asked regarding the periodic trend. So we'll just see that and do some 10 previous year questions and wind up this chapter. So please open your notebook, take a pen and make notes with me so that you can avail all the important notes from this chapter in one particular place. Okay, so let's get started. What all topics we have here? The first topic that we are going to discuss is the genesis of periodic table, that is how the periodic table was developed. All of you know, first Dobrunov triad came, then law of octaves, then Mendeleev periodic table, modern periodic table. So what were the flaws, what were the advantages of these periodic tables, that we will see. Then nomenclature of the elements greater than 100, what is the rule followed there. Electronic configuration and periodic table. So how by seeing the electronic configuration you can guess the position of the element, that we will see. Next, electronic configuration and type of element. So from the electronic configuration, how can you predict which block element, that also we will see. And this is very important, from where the questions will be asked, that is your periodic trends. Okay, now these all things will go little fast and here I'll take time and here I will invest more time because this is the most important part. Now coming to weightage, you can see one or two questions in 2022, 3 questions were definitely asked, but after that the graph has been very flat. So genesis of periodic table, what all things we have? Dobrunov triads, Newland octaves, Mendeleev's and modern periodic law. Okay, so what does Dobrunov triad say? That he was able to make elements in pairs of, in groups of 3, and the mass of the middle element was the average of the other 2 elements, right? So you can see Dobrunov triad example, lithium, sodium, potassium. So 39 and 7 if you add, it comes to around 46, right? 46 divided by 2 is 23. Similarly, carbon, strontium and barium, if you solve, if you add 137 and 40 and divide by 2, you will get 188. The same thing appears here, right? So that is what, in each case the Dobrunov noticed that the middle element is the average atomic mass of the other 2 elements. So you have to remember these 3 elements, what all examples are there in the Dobrunov triads. Next, what were its limitation? It could work only for few elements. So you can say 1, 2, 3, 4, 5, 6, only 9 elements was considered in this, and all the elements could not be put in this one category. Okay. Next, if we see Newland law of octaves, so he arranged the element in the increasing order of their atomic weights. Okay, so he just gave the elements in the atomic weights and found that the properties of the 8th element is similar to the properties of the first element, and he thought that it is similar to the musical notes. How you see, if you know the musical notes sa, re, ga, ma, pa, dha, ni, and after that again the sa comes, right, which is the repetition of the first note. So every 8th element has the property similar to the first element. So that was what told by Newland law of octaves, and you can see here lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and the next element sodium has the properties of lithium. Now here a question may arise that, ma'am, after fluorine neon comes, but at that time when Newland gave this law, so sodium was not discovered. Okay, then sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and after that you have potassium, which is having properties similar to this one. Okay, next, what were the limitations here? It was applicable only till calcium. Okay, so this 8th element that he was able to make, it was applicable only till calcium. After calcium, this was not followed. Okay, this trend was not observed. Next, we have our Mendeleev's law. Okay, so Mendeleev says that the properties of the elements are the periodic functions of their atomic masses. So what he did, he just arranged all the elements in their atomic masses, and he found that, and the periodic table that he made, it consisted of 7 horizontal rows, which we call that period, and 8 vertical columns known as groups. Now each of these vertical group was divided into category A and B, and the elements are arranged in the increasing order of their atomic masses. Elements with similar chemical properties are placed together in a group. Okay, so that is what was your Mendeleev periodic table. So you can see here that 1, 2, 3, so we have 1, 2, 3, 4, 5, 6 and 7. So you have here 7 horizontal rows and 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. You can see here 8 vertical columns are there. Okay, and he placed the elements according to their atomic masses. Now, what were the good things about this periodic table? So he could easily predict the new elements. So suppose there was one element, so he left some gaps for the few elements which were not discovered at that time, and he predicted that in future certain elements will be discovered which will fit this place. Okay, that was the most important thing, and he Mendeleev called these unknown elements as Eka aluminium and Eka silicon. He also predicted the properties of these elements. Okay, hence the Mendeleev periodic table led to the discovery of new elements. He said that okay, there is no element where this property is matching. He didn't put any other element there. He thought, okay, if there is no element which is matching this property, let's leave a vacant place there. In future some element will be discovered and it will be kept there. Okay, and next is systematic study of elements. Since all the elements were arranged in tables, so it was very easy to study them. Okay, next merit was your correction of doubtful atomic weights. Now, based on the chemical similarities, he corrected the atomic weights of few elements like beryllium from 13.5 to 9. Okay, so he also corrected the atomic weights. Next we have what are the demerits. So anomalous position of hydrogen, so that is still there. For hydrogen we cannot have any proper position because its electronic configuration is similar to metals and its properties are similar to non-metal. So hydrogen is placed in the middle of the periodic table. Next, anomalous pair of elements. So some elements with higher atomic masses precede the elements with lower atomic masses. So he arranged the elements in the increasing order of their atomic masses, right? But somewhere where the properties were not matching, the elements which were having higher mass were kept before the elements which are having lower mass, right? For example, if you see argon, molar mass is 39.9, precedes potassium whose molar mass is 39.1. So first argon comes, then potassium comes. Similarly, you can see cobalt 58.9 precedes nickel which mass is 58.7. So these were some of the anomalies. Next also we have here position of isotopes. So because isotopes masses are different, right? So according to his rule, because atomic masses was the main criteria in which the elements were arranged, so if isotopes should be placed at different places in the periodic table according to their atomic weights, right? Next we have dissimilar elements. So some dissimilar elements are grouped together while some similar elements are placed in different groups. This is one of the most important demerit and you should know the examples for this one also. See, alkali metals such as lithium, sodium and potassium etc. were kept in group A, are grouped together with coinage metals like copper, silver and gold whose properties are not similar to lithium, sodium and potassium, but they are kept together. And at the same time certain chemically similar elements like copper and mercury have been placed in different groups. Okay, so this was an anomaly that same property elements were kept in different groups, different properties elements were kept in same group for certain elements, not for everyone. Okay. Next we have last here position of the elements of group 8. So no proper position was given to the elements of group 8, that is these 9 elements which have been arranged in 3 triads, 4th, 5th and 6th period without any justification. Okay, so there was no reason why. I can show you that table. Yes, so you can see here in the argon is kept here, krypton, xenon, helium. So there was no justification why these elements are kept here. Okay, so that is the demerit here. So next we have even the positions of lanthanides and actinoids, where the 14 elements following lanthanum from atomic weight 58 to 71 and another 14 elements from atomic number 90 to 103 have not been given proper position in the main frame of the periodic table. Okay, so there was no proper position for these periodic table elements. Okay, now if I see the next law that came was your modern periodic table, and according to modern periodic law, the physical and the chemical properties of the elements are the periodic function of their atomic numbers. Okay, Now, in modern periodic table, elements are arranged according to their electronic configuration and atomic number. Okay, so there is nothing related to atomic masses. It was done according to the electronic configuration and the atomic number. Here also we have 18 groups and 7 periods. Okay. So now you can see the first period is hydrogen and helium, number of elements is 2. In the second period you have lithium to neon, number of elements is 8. Third period sodium to argon, again 8. In the fourth period we have potassium to chromium, 18 elements. Fifth period we have Rb to Xe, 18 elements. Sixth period Cs to Rn, 32 elements, and seventh period is incomplete, starting with francium. Okay. Now this is the entire periodic table. You can see first period, second period, third period, fourth period. So in the fourth period we have first, second, third, fourth and fifth we have 18 elements, right? So this is fourth 18 elements, fifth 18 elements, sixth also 18 elements, right? 1, 2, 3, 4, fifth, sixth we have 32 elements. Okay, so why this 32 comes? So you can see here 32 elements because this is also included. Okay, and francium is incomplete, so that is why that is not counted. Okay, so next we have the nomenclature, how to name the elements having atomic number greater than 100, greater than 100. So you have digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The name that is used for this is nil, un, bi, tri, quad, pent, hex, sept, oct and n. Okay, and the abbreviations that is used is their starting letters. Okay, so nil for 0, un for 1, 2 for bi, and tri for 3, quad for 4, pent for 5, like this. So now suppose you have a number 101. So for 1 I will write un, for 0 nil, again for 1 un, and the name will end with IUM. So the nomenclature of this one will be UNU. Okay, next if I have 102, so it is un, nil, bi, then UM, so UNB. Okay, so these are how the numbers are named after 100. Okay. Next we have here the most important part, that is electronic configuration and periodic table, electronic configuration and type of elements, and I will discuss about the periodic trends that you can see. There are almost 6 periodic trends about which we will be discussing. Okay, so first coming to electronic configuration and periodic table. So the period indicates the value of n for the outermost shell or the valence shell. So the element is in which period? Okay, that you can easily say by saying the valence shell of the electron. Like for example, if I have for example, if I have an element sodium, what is the electronic configuration of sodium? 1s2, 2s2, 2p6, right, 6, 7, 8, 9, 10, 3s1. So if I see the valence shell n is equal to 3, so that means it belongs to the third period. Okay, so by seeing the valence shell you can easily predict the period of the element. Next, electronic configuration in the group. So elements in the same vertical column or group have similar valence shell electronic configuration, the same number of electrons in the outer orbital and the similar properties. So now if you see that if the number of, so group can be denoted by the number of electrons in the valence shell. Number of electrons in the valence shell. So for if it is 1 and 2, that is fine. Okay, if it is more than 1 and 2, so I will tell you example. So here I can say that it is from first group. Okay, now let me take one example of nitrogen. For example, nitrogen, what is electronic configuration? 1s2, 2s2, 2p3, right? So what is the last shell? N is equal to 2. That means I can say that it is your second period element. Okay, next here we have total valence electron is 5. Okay, so if it is more than, like if the total number of electrons you get 3, 4, 5, 6, 7, then you have to add 10 to that. So if I'm getting 5 here, so group number will be 5 plus 10, that is 15. Okay, similarly, so by seeing the electronic configuration you can easily predict the group number and the period number. Next we have electronic configuration and type of elements. So if the electron enters the last electron, as you see in here, the last electron is in s orbit, right? So that means it belongs to s block. So the periodic table is divided into 4 blocks. So if I show you the periodic table, where is it? Just a minute. Yes. So the first 2 is your s block. These are your p block. Okay, this middle blue one is your d block, and the bottom 2 is your f block. S block, p block, d block, f block. Okay, so if the electrons enter to the s orbital, the last electron, then it will be either a member of group 1 or group 2, right? So group 1 and group 2 are from s block, group 13 to 18 are in your p block, and group 3 to 12 is your d block. Okay, so now if I see this one, okay, so if the last electron enters to the s subshell, then it is an s block element. It has now 2 groups, that is your group 1 and group 2. So group 1 general electronic configuration is ns1, and group 2 general electronic configuration is ns2. Okay, and these are considered as metals and are very highly reactive. Now we have, if it enters to the p orbital, then here we have group number 13 to 18. Okay, so how many? 13, 14, 15, 16, 17, 18. So there are 6 groups present in group p block. So p block we have, in p block I have 6 what I can say 6 groups. Okay, that is from group 13 to 18. Okay, now the electronic configuration varies from ns2 to np1 to 6, ns2 to np1 to 6. Okay, and the group 18 elements are your noble gases, and here are some special names given. Group 16 is called as chalcogens, group 17 is called as halogens, and you should know one more thing here, group 15 is called as your pnictogens. Okay, next now total s block and p block elements are together called as your representative elements. Okay, next, if the element enters to d orbital, then it is a part of d block elements. So here we have group 3 to group 12. So total how many groups are there? Total 10 groups are there. Okay, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Next, the differentiating electron enters the d subshell, the general electronic configuration you might have studied in the d block chapter also, n-1d 1 to 10 ns2. These elements are known as transition elements. Their properties lies between the p block and s block, so we call it as transition elements. Okay. Next, similarly in f block, the last electron enters to the f orbital. Okay, and here we have 2 rows, that is your lanthanoids and actinoids, and these are known as inner transition elements. Okay, so we have lanthanoids and actinoids, these are called as inner transition elements. General electronic configuration n-2 f1 to 14, n-1 d0 to 1, and ns2. Okay. Next, the most important thing we'll discuss, that is your ionic radius or atomic radius. So along the period it decreases, down the group it increases. Okay, so please remember, if you have along the period, it will, so this is your lithium, beryllium, boron, carbon, this is along the period, so it will decrease. And if you have along the group lithium, sodium, potassium, rubidium, cesium, so it will increase down the group. Okay. Next, I have okay, one second. Okay, next term we have here is ionization enthalpy. So ionization enthalpy, if you see, okay, ionization enthalpy along the period, okay, along the period, what happens? Ionization enthalpy increases, and down the group, we have ionization energy decreases. Okay, along the period ionization enthalpy will increase, down the group ionization energy will decrease. Now the amount of energy required to remove one electron from the outermost cell of a neutral isolated gaseous atom is nothing but your ionization enthalpy. Now once you have removed the first electron, when you remove the second electron, that is your IE2, and IE2 will always be greater than IE1. Okay. Similarly, IE3 will be greater than IE2. Now, what are the factors on which the ionization enthalpy depends? So, here we have, these are very, very important factors. Yes, so atomic size. If the atomic size will increase, ionization enthalpy will decrease. So, that is why what happens down the group, if I move down the group, size increases and ionization enthalpy decreases, right? That is what I have given you here. 1 second. Yes, down the group ionization enthalpy decreases, right? Why? Because the size is increasing. Next, nuclear charge. So, nuclear charge, if it increases, the ionization energy will increase. This is very conceptual. So, understand, if the last electron is there, if the nuclear energy is very strong, that means it will hold the electron very tightly. To remove the electron, we will require more energy, right? So, if we require more energy to remove the electron, ionization energy will increase. The third one, screening effect. If the screening effect will be more, then ionization energy will be also less. Why? See, if screening effect is more, that means what? Understand this one properly. So, we have here nucleus and we have the valence electron. Screening effect means, just imagine there is a screen here, okay? If screening effect is very good screening effect, that means what? This nucleus is not, like there is a blockage to this nuclear force, right? So, I can say that this electron is less attracted or less tightly held by the nucleus, right? So, if this is less attracted or less tightly held by the nucleus, then what will happen? This force of attraction is very weak, we can easily remove this electron, so ionization energy will decrease. If screening effect is very strong, okay, then ionization energy will be less. If poor screening effect, that means this is not a good screening effect, okay. So, I will just draw like this. Suppose it is a weak screening effect, then this force, nuclear force will be very strong. That means removal of electrons will be difficult, okay. Next, type of electron. So, type of electron, so that is also, if the electron is in 4s orbital, then ionization, like any s orbital, then ionization energy will be more. If the electron is in f orbital, then the ionization energy will be less. Because of the shape, 4s orbital, sorry, not 4s, any s orbital is very close to the nucleus, okay. So, nuclear force is very high, so ionization energy will be very high. Next one is important here, electronic configuration, half filled and fully filled. So, if we have any half filled configuration or fully filled configuration, then nothing will matter. If it is half filled, then its ionization energy will be more, okay. Here we have example for this, exceptions that you should know, beryllium and boron. So, in the second period element, what all things we have? I have lithium, right, beryllium, boron, carbon, nitrogen, oxygen and fluorine, right. So, if I see along the period, what happens? Size decreases, so ionization enthalpy will increase. That means beryllium should have the electronic configuration like this. This should be the order of ionization and enthalpy, right. But here what we observe is there is a change. Lithium is there, after that boron is there, after that beryllium comes, then carbon comes. What is the reason for this change here? The electronic configuration. If you see beryllium electronic configuration, it is 1s2 and 2s2. Completely filled orbital is there, so removal of electron from here will be very difficult, right. Beryllium electronic configuration, so its ionization enthalpy increases. So, you can see here electron is removed from 2s orbital. Similarly, we have an exception for nitrogen and oxygen. So, if you see carbon, nitrogen and oxygen, right. So, along the period size decreases, so ionization energy should increase. So, this should be the order. But if I see nitrogen electronic configuration, it is 1s2, 2s2 and 2p3, right. And this 2p3 is what? It is exactly half filled. Okay. Now, because it is half filled, it is a stable electronic configuration, and that is why here pulling of electrons will be difficult, and nitrogen ionization enthalpy is more than that of oxygen. So, these are some exceptions that you should be knowing. Next we'll come to electron gain enthalpy. So electron gain enthalpy is the amount of energy that is released, okay, when one electron is added to an atom. That's the definition. Amount of energy released to add an electron to the outermost shell of the neutral isolated gaseous atom. It is generally exothermic, okay. When you add one electron, you have to like energy is released, so that is why it is an exothermic process. Now EA2 and EA3 will always be positive. Now see, suppose I have a neutral atom, okay, I added one electron to this one, so it became A minus. Now this process, to add one electron, we have to, energy will be released, so it is an exothermic process. Now already when it is A minus and you want to add one more electron to this one, so there is already an anion, to that you are adding a negatively charged, so there will be repulsion. So you have to provide energy in that case, and after this when it becomes A2 minus, it is endothermic. Okay. Now group 17 elements have the highest negative electron gain enthalpy because of their small size. They can easily gain electron and they have the highest electron gain enthalpy. Now electron gain enthalpy becomes more and more negative as we move from left to right along the period. Okay, so as we move from left to right, the electron gain enthalpy will become more and more negative. Now more negative means increases along a period, okay, less negative down the group. So down the group what happens, the electron gain enthalpy decreases, so it becomes less negative. Here is an exception. So if I see fluorine, chlorine, bromine and iodine, right, so down the group the electron gain enthalpy should decrease. So suppose this is -3, then they should become -2, right, but exactly what happens, the order is like this: chlorine, fluorine, then bromine and then iodine. So chlorine is having more electron gain enthalpy than fluorine. Similarly oxygen is having less electron gain enthalpy than sulfur. Now the reason for this is small size of fluorine, okay, and due to this small size of fluorine there is inter-electronic repulsions, okay, inter-electronic repulsions are there, and that is why the fluorine electron gain enthalpy is less negative than that of chlorine. Clear? Okay, next, electronegativity increases along a period. Okay, size is small, so electronegativity will increase down the group because the size is increasing, so the electronegativity will decrease. Next, what is diagonal relationship? This is very important. Which elements are having diagonal relationship, that also you should remember. So the diagonal relationship is a phenomenon observed in the periodic table where certain elements in the second period show similarities in properties with the elements in the third period. So you should know that second period element and third period element, diagonal elements have some similarities in their properties, and this is called as your diagonal relationship. Okay, now if I show you examples you can see here. Yes, lithium and magnesium, beryllium and aluminium, boron and silicon. Okay, so first let us locate them in the periodic table. So what all things we have? Lithium, magnesium, beryllium, aluminium and boron, silicon, right? So let us observe them in the periodic table. Yes, lithium and magnesium, diagonal element, okay. Then I have beryllium, one second, yes, beryllium and aluminium, okay. So if you just imagine this is not there, then beryllium and aluminium again diagonal elements, boron and silicon again diagonal elements, right. So these properties of lithium and magnesium are similar, beryllium and aluminium have similar, boron and silicon have similar properties. So that is why they are called as diagonal elements or diagonal relationship, okay. So let us see what properties are similar in these elements. So first of all, if I see lithium and magnesium, both form nitrides, okay. They both can form nitrides, both form stable covalent compounds, okay, that is their similarities. Now if I see beryllium and aluminium, they both form aluminium amphoteric oxides. So amphoteric oxides are those oxides which can show both acidic and basic properties, right. So they show amphoteric oxides, they both can form complexes, okay. So that is their similar properties. Now boron and silicon, what properties they have? They both form covalent hydrides B2H6 and SiH4, and they can both form acidic oxides like B2O3 and SiO2, Okay, so these are certain properties that you should be knowing, and this is very important. The beryllium oxide and aluminium oxides are amphoteric in nature. Next, anomalous properties of the second period of elements. So it is a common observation that the second period elements have different properties as compared to the elements of the other elements in the same group. For example, if I talk carbon family, that is group 14, right? So group 14, carbon specially will have a separate properties, and carbon, then leaving carbon, silicon, germanium will have some other properties. So every second period element shows a different property compared to that of the other elements of the same group. Now what is the reason for that? There are certain very obvious reason for that. The first reason is that is this, they are very small size compared to the group. These are the elements which are the smallest in the size. They do not have any d orbitals. Okay, their d orbitals are absent, so there is a very huge difference in their bonding pattern. Whereas the next elements can form 5-6 bonds, the first element can only form 2 bonds, 3 bonds based on their electronic configuration. So the covalency of these elements are restricted. Okay, next we have high charge to size ratio. Okay, their size is very small, so charge to size ratio is very high. So these are the different reasons due to which they show some anomalous behavior, or you can say some unique behavior compared to the other elements of the group. Clear? Okay, now we will see some questions. Okay, some examples we will see that are like how I can say that these form different properties. Some examples we have: lithium and beryllium form compounds with pronounced covalent character. Okay, so if you see lithium and beryllium, both are the first elements of the group, they form pronounced covalent character compounds, whereas the other elements form ionic compounds. Okay, if you see sodium will form ionic compound, magnesium will form ionic compound, but lithium and beryllium can form a good covalent character compound. Next, if you see, the maximum covalency of the first member of each group is 4. Okay, boron can form only 4 bonds, whereas the other members of the group can expand their valency to accommodate more than 4 pairs of electron, example aluminium. So if you see boron and aluminium, right, these are of the same group, right? Boron can form only 4 bonds, whereas aluminium can form 6 bonds, and that is due to the absence of d orbital in boron. Next, if you see, the first member of the p block elements displays greater ability to form p pi multiple bonds itself. You can see we can have carbon carbon bond, carbon carbon, nitrogen bonds are there, and to other second period elements compared to the subsequent members of the same group. So you can find this multiple bond formation within the second period elements only. The next period elements, that is down the group, if we move the elements, cannot form multiple bonds. Okay, so that is another property that we can observe. So what are the anomalous property we saw? One example is your lithium and beryllium. These are metallic, right, group 1 and 2 elements, so they generally should form ionic compounds, but we have found that these 2 elements can form proper covalent compounds. First anomaly. Second one that we observed is the covalency of the first element is maximum 4. Boron and aluminium, if we talk, boron can form only 4 bonds, whereas aluminium can form up to 6 bonds due to the absence of d orbital. Another property or another anomalous property is that the second period element of the p block, we are not talking about s block, so lithium, beryllium are excluded. If you compare carbon, nitrogen, oxygen, these can form multiple bonds among themselves and with the other elements, but the other elements of these groups, carbon group, that is your silicon, nitrogen, phosphorus, so they cannot form multiple bonds with each other. Okay, so these are the 3 anomalous behavior that we can see. Okay, now we will do some previous year questions. The correct order of first ionization enthalpy of the given element is. So we know along the period ionization enthalpy should increase, so lithium should be the least one, right? So I told you there is an exception between boron and beryllium, so option number A here, right? Boron is having, beryllium is having 2s2 configuration, completely filled configuration, so to remove one electron from here it will become difficult, and that is why the beryllium electronic configuration or the beryllium ionization energy will be maximum, will be higher than boron, even if the size of boron is smaller. Okay, if you follow the general trend, we have lithium, beryllium, boron and carbon. Along the period, size decreases, so ionization enthalpy should increase. So this should be the order, but here because of the electronic configuration there is a small change. We will get like this. Okay. Next, the property of halogens which is not correctly matched. So halogens means your group number 17. Okay, we call them as halogens. So density, as we go down the group, so what are the elements in group 17? Fluorine, chlorine, bromine and iodine, right? As we move down the group, mass will increase, so definitely density will increase. So iodine will have the maximum density. This trend is correct. Electron gain enthalpy. So I have told you this is an exception. So generally the electron gain enthalpy decreases down the group, but chlorine will have more electron gain enthalpy than fluorine because fluorine has small size, right? Due to this small size there is inter-electronic repulsion. Inter-electron repulsion, right? So that is why the correct order is chlorine, then fluorine, then I have bromine and iodine. Okay, so this is the incorrect one. Next, elements X, Y and Z have the atomic numbers 19, 37 and 55. So if you see, these are the elements of the same group. How can I say? See, if I add 19 plus 18, right? So if I add 18 here, so I will get 37, and if I add here again 18, right, so I will get again 55. So these are the elements of the same group. So ionization energy, if I talk, then down the group what happens? Ionization energy decreases, right? So if this is X, this is Y, this is Z, the ionization enthalpy order will be X, then Y, then Z. Okay. Now the question is, Z would have the highest ionization energy. No, Z will have the lowest. So this is the wrong statement. Next, Y would have the highest ionization potential. No, it is in between. The ionization potential would increase with the increase in atomic number. Now if you see, the atomic number is increasing, but the ionization potential is decreasing. So this is also wrong. So Y would have an ionization potential between X and Z. Yes, that is correct. So option number D is the correct answer. Next, amphoteric oxides among the following. So I have given you beryllium oxide is amphoteric, right? Beryllium and aluminium oxide. The third ionization enthalpy is highest in. So if we talk about third ionization enthalpy, means removing the third electron will be difficult in which case? So that is your alkaline earth metal. Alkaline earth metal represents group 2. Okay, alkali metal represents group 1. So if I see group 2, for example, magnesium. Okay, atomic number is 12. So 1s2, 2s2, 2p6 and 3s2. So if I want to remove the first 2 electrons, I will remove. When I am going to remove the third electron, it is from a stable configuration, right? The valence electron is already 8. It is a very stable noble gas configuration. To remove the third electron from here will be very difficult. So it will be very high value. So answer is option number B here. Next, the first ionization enthalpy of the following elements are in the order of. Okay, the first ionization enthalpy. So what all elements are given to me? I have carbon, silicon, I am just writing, then I have nitrogen and phosphorus. Okay, so if you know, along the period the ionization increases, down the group ionization energy decreases, right? So I have to find in this order. So if I see first the lowest one, okay, lowest one will be silicon. Down the group it is decreasing, that means it is less than carbon and silicon, and along the period it is increasing. So silicon will be the least one. After that I have phosphorus, and again here I have carbon and then nitrogen. So option number D here. Okay. Next, which of the following is the correct order of radius? So always remember, first anion will be more size, then a neutral atom, okay, then you have the cation size. Okay, in anion more is the charge, more charge, more size. Okay, in cation more charge, less size. Okay, clear? So now you see here anion should have the highest size, but this is wrong. Here this is correct, anions are greater but more charge means more size, but here it is again less. Here cations are given at the first, so it is also wrong. Negative, neutral, positive, option number A here. Okay. Next, which of the following would exhibit amphoteric oxide? So beryllium and aluminium we have discussed, option number B. Next, the electronegativities of carbon, nitrogen, silicon and phosphorus. Same thing again, carbon, nitrogen, silicon and phosphorus. So we have to see that along the period what happens, electronegativity increases, right? So these are having less than this two, right? Now after down the group again electronegativity decreases. So here this side it is increasing and this side it is decreasing, right? So I can say that silicon and phosphorus are having less electronegativity. So again silicon will come first, right? After that phosphorus, after that phosphorus. Out of carbon and nitrogen, we know that nitrogen is more electronegativity. So option number A here. Next, this is important question. For one of the element, various successive ionization enthalpies are given. Okay, the element is. So here what I can say is, first ionization enthalpy was 577, then after that second was 1810, then 2750. But when I see the fourth element, if I am going to remove, it is having a very huge difference. You can see 2000 to 11,000, right? The jump has been very high. So that means what I can say, after removing 3 electrons, the element must have got a noble gas configuration. So which is that element where after removing 3 electrons I got a noble gas configuration? So if I see aluminium, okay, so aluminium electronic configuration is 1s2, 2s2, 2p6, and then I have 6, 7, 8, 9, 10, 3s2 and 3p1, right? 6, 7, 8, 9, 10, 11, 12, 13. So after I have removed these 3 electrons, I1, I2, I3, I have the configuration 1s2, 2s2 and 2p6. This is a noble gas configuration for neon, right? So now here what happens, if you see 6, 7, 8, 9, 10 total neon. So from here if I remove one electron, the fourth electron, it will require very high energy. So option number D is the correct answer. Okay, so yes students, these were some PYQs as well as the basic concept of the chapter. You can easily study this chapter, very few, half an hour to 1 hour is maximum for this chapter, then solve the previous year questions. I will also be coming up with top 30 questions from this chapter in the top 30 series soon. Okay, so if you have any doubt, please put down in the comment section, and how you like the session, was it good or not, was it helpful or not, what else can be done, that too also you can put. And always remember, our target is 60 out of 60 in KCET chemistry. So that also put hashtag 60 out of 60. Let me see how many of you are interested or how many of you are motivated to get that full marks in KCET chemistry. Thank you students. See you soon in the next class. Do not forget to subscribe the channel.